speaker is Kingman Cheung. The title is Measuring Properties of a Heavy Higgs Boson in the Higgs 2GZ 2 for lepton decay. Please start.
Good afternoon, everyone. So, I hope you all have a good lunch, although the time is very short. Okay, so let me talk about one thing which is sort of different from the morning. I'll talk about measuring the properties of heavy Higgs boson in this decay. Higgs go to 2C boson is 4 charged leptons. Of course, this is at this point hypothetical. Okay, we haven't seen the heavy Higgs bosons. What we see is our new friend, the Higgs boson 125 GeV. But I'm talking about another one. If we see another one, how we determine the CP properties of it. And this is the work done with Zhang Yong, Jason Lee, Ji-Ting Lu, and Jubin Park. So I have a very brief story of the Higgs bosons. Okay, of course, we all know the Higgs boson was proposed in 1960. So it took about almost 50 years before it can be discovered. Now, as you know, that gravitational wave was proposed 100 years ago. We take 100 years to discover that. Now, you can guess what could be the next. Okay, supersymmetry maybe take 200 years before we can discover it. But I hope it can be shorter so that we can see it in our lifetime. And the story of Higgs boson is very simple. Now, the Higgs boson is our key understanding of the origin of mass. Of course, the origin of mass is ultimately connected to electroweak symmetry breaking. Now, we all know that before electroweak symmetry breaking, everything is massless. The whole universe is filled up with a Higgs field uniformly throughout the whole universe, and every particle is massless. Now, what's wrong with that? Every particle is massless. Now, as you know that from special relativity, when a particle is massless, it has to be traveled at the speed of the light. So an electron traveling at the speed of the light, and the atom also traveling at the speed of the light, it cannot catch it. So we cannot form atom. Without atom, we cannot be formed. Well, our human being also cannot be formed. All right. So, by some reason, that is the Higgs field will develop a vacuum expectation value. All right. And everything, the particle that should have mass will develop a mass. Now, then the electron develop mass, and the electron being captured by the atom, it will form a atom, and then form molecule and so on. And this is the origin of mass. But still, there's something missing from the standard model. Is that how and why this Higgs field develop a wave? Okay, that's a very deep question of electroweak symmetry breaking. Now, we know that now Higgs boson has been discovered. It is the evidence that the electroweak symmetry breaking did actually happen. Okay. Now, the current question is it all? What else that we can expect from the experiments? So the motivation of this talk is that standard model with one Higgs doublet is not natural. This is my starting point. Someone may argue that why not? Just one doublet is simple. But, well, for some people that are working on beyond standard model, we know that it's not natural. Now, we expect some heavier Higgs boson should appear very soon. Okay? Well, how soon is soon? We don't know that. We expect it happen in the next 10 years. Now, actually, Eric C. has been searching for heavier Higgs bosons through a pair of gauge bosons, like a pair of Z boson, and then decay into 4 charged leptons. And actually, when you look at some data, you can see some 2 or 3 sigma here and there, 240 GeV, 600, you can name it. Whatever they see a bomb, people get excited. One famous example, almost 2 years ago, is 750 GeV. I guess most people have written at least one paper on the subject, but it go away. Nowadays, people are more careful. But recently, some people are very excited about 1.4 TeV they see in the electron spectrum. Now, okay, so we keep our eyes open in the data. Okay. Now, so we are going to talk about. Suppose we see a heavy Higgs boson through this decay. We try to investigate the CP property of these bosons.
Question.
Yes.
Are you going to explain why one Higgs doublet is not natural later?
It's not what?
No, you like in the beginning you like one Higgs boson doublet is not natural. Are you going to explain this or?
Well, this is like a personal opinion. People may think that the gauge hierarchy problem is a good reason that the standard model with one Higgs doublet is not natural. We need something to stabilize the Higgs boson mass, like supersymmetry. And for supersymmetry, we need at least 2 Higgs doublets. So we expect something soon, actually. We should expect something soon. I hope we do not wait for 100 years. Now, so these are the general form of couplings that I'm trying to look at the moment. This is a general vertex for a Higgs boson coupled to a pair of C bosons. And this part, just like the standard model part. The second part is due to some higher order corrections. This is CP conserving. Finally, the third part is, this is CP even, this is CP odd terms that we try to look at. We try to using the data, suppose we see some data, how well we can constrain these 3 couplings. All right. Now, and in general, these form factors can be complex if some absorptive part is being developed. Okay. Now, I hope you will not feel it boring, but I just go through it very quickly. Okay. So, this is some like graduate school, the first class on the helicity amplitude. Like Higgs boson decay in a pair of C bosons, and then decay into 2 pair of fermion. You can say leptons. All right. So the first part concerning the decay of the Higgs boson into a pair of C bosons, and then a pair of propagator, the first C boson propagator, second C boson propagator. And these 2 are the decay amplitude of the C boson into the charge leptons. So basically you can put it into 3 parts. One is the first part, Higgs go to the pair of C propagator, and the C decay into a pair of fermions. Okay? Should be simple enough. By then, we can include all the spin correlations. So, so we'll define the what we call the helicity amplitude, the plus helicities, minus helicity, and the longitudinal. Now be careful, when we define helicity, we have to find a frame, all right? Because with different frame, helicity may have some different meanings. So we are defining the rest frame of Higgs bosons. Okay? This is what I learned in my graduate school. Where should one define the polarizations of the gauge bosons? Okay. We define in the rest frame of Higgs bosons. All right. So we have plus and minus and the 0. One thing I want to point out that this longitudinal mode actually get enhancement when energy goes up. So I have one parameter here, alpha I, which is ki squared over mx squared. Basically, when this is the ki squared, which is the mass of the C bosons, and m Higgs. And when the Higgs getting heavier and heavier, this alpha becomes smaller. When it gets smaller, so this factor actually get enhanced. So that's how the longitudinal component keep being enhanced by when the energy goes up. So I have a form here. So enhanced by a factor of mx squared over 2 masses squared in large mx limit. So now I do not bore with the first part. So basically, combine everything into Higgs boson, you get 2 C boson, and then 4 charge leptons, and then labeled by these helicities of the charge leptons, I arrive at this equations, the longitudinal part, transverse part, and the longitudinal part. Now, I do not bore you with this one, but just point out this final expression that I'm going to use. So I'm going to square the amplitude and sum over the helicities, so I end up with 9 combinations of the angles. Okay. Now, at this point, you don't have to care about that. And with the coefficient Ci. Now, Ci is those plus and minus amplitudes, and some of them will enhance when energy goes up. So I have 9 combinations of the angles, and the angles are given in this diagram. Okay? So that basically the Higgs bosons, X represent Higgs bosons, decay in the pair of C bosons, and then in the rest frame of each C boson, decay in the pair of charge leptons. And the angle, like theta 1, is the angle that the charged lepton made with the direction of the C boson, and also the phi. Okay. And these two planes are separated by the angle capital phi here. Okay. So everything will be expressed in terms of these angles. Now, and the coefficient are given by that, C1 up to C9. We have 9 combination of angles, so I have coefficient C1 to C9. Now, there are some CP properties that we can look at this coefficient CR. So we can look at the CP and CP tutor, CPT tutor, and the CP, lambda go to minus lambda. Now, under that, you can see, for example, this become minus and this become plus. So this become negative. So overall, we have C2, C5, C6, and C9 CP all. And actually, they will be non-zero when both the CP odd part and the even part coexist. Okay? And the other one, C2, C6, C7 are CP tutor odd. Okay? And they will be non-zero when they develop absorptive parts. So I can look at the decay width distribution now, okay, with these angles. So overall, I just look at this expression. So this is normalized distributions with respect to the cosine theta 1, cosine theta 2, and this angle phi. All right, I can written in terms of this Ri. Now this I count it as some kind of observable in experiment. Experiment you can measure, and this Ri is given by these expressions. All right. Now, once I have a distributions, I can fit it to this Ri. Okay. Now, in the following, I'm going to use some narrative approximations, such that all C both are being unsure to make it more simple to understand it, for understanding. All right. So, in this distribution, I have the 3 variable, theta 1, cosine theta 1, cosine theta 2, and phi. Now, we can integrate either 2 of them to get easier expressions, like d sigma d cosine theta 1. After integration, I only left with 3 observable, R1, R2, and R3. So once I measure this cosine theta distribution, I can fit to this R1, R2, and R3. And the phi depends on R4, 5, 8, and 9. All right. Now, overall, the width is decay in written in terms of C1 plus C3. Now, I just simply take this omega W1, W3 group. All right. So at the end, we find that C1, C2, C3, only these 3 coefficients contribute to distributions. Okay. So once we have the cosine theta 1, cosine theta 2 distribution, we can fit to this R1, R2, R3. Now, and also, when the C2, one of the coefficient is 0, and then which means that these 2 are real, then this R2 will get 0. Now in these 2 expressions, you will find that there are no R6 and 7, these are missing. Now this is missing, so in this one-dimensional distribution, we cannot see them. Okay, so in order to see that, we have to go to like 2-dimensional distributions. Okay. So this angle observable R1, 2, 3 can be obtained by fitting to cosine theta 1, theta 2 distributions. And the other 4, 5, 8, 9 can be obtained from Fourier analysis or from fitting to the phi distributions. Now here, if we see a non-zero R2, which implies there must be some new particle of mass less than the Higgs boson, half of the Higgs boson mass that are running in the developed absorptive part. Now, measurement of Ri itself cannot determine absolute value, because what we have here is just a normalized distribution. So when we do not get the absolute values, we just get the relative values. Okay? So we also need to measure C1 plus C3, this partial width. Actually, we can count the number of events that we can see in the experiment. So let me come to the numerical analysis. I'm just using an example of 260 GeV Higgs bosons. Now, for 260, all these 3 moles are comparable. Okay? And the branching ratio for TT bar is 0 or almost 0. Okay? Now, when we work on the paper, there's some rumor that 240, there's some 2 or 3 sigma excess, but well, we just keep it at 260. Now, for this case, these 2 coefficients are basically real. Okay? So there's only 3 input parameters of the couplings that we have to pay attention to. So these are 6 scenarios that we are looking at. So we have these factors, 0.1 and the other 0. These are very simple case. And the other 0.1, 0.1 here. And S4 is 0.1, 0.1. Because they simultaneously coexist, you can see some CP violations. All right. And S5 too. Now S6 I'll give, for S6, I'll do more detailed numerical simulations. So these are the coefficients that we actually can calculate. Once you're given these coefficients, and you know the energy and the masses, and then you can actually calculate the coefficients. Okay. Now this coefficient, and then we input this coefficient into a Monte Carlo to get out some real data, and then fit this data to get how well we can fit, how good that we can determine this coefficient. All right. So S1, 2, 3, as I have said, this CP conserving because only one couplings are non-zero. 4 and 5, they are the CP even part and CP odd part coexist. That means CP are violating. And S6 are chosen, they contribute more or less the same. Okay, so these are the coefficients that I just mentioned, R1 to R9, R1, R2, R1, R3, and R4, 5, 8, 9. Okay, all the other like 5 and 6 do not appear in this one-dimensional distribution. So these are the curve. There's these 3 CP conserving cases. I have the cosine theta distributions, okay? And this 1, 2, 3, and the cosine theta distribution, and also the phi distribution. Okay, they're all CP conserving, so it's symmetric about the 0. For the 4, 5, 6, they are CP violating. Actually, you can see it is not symmetric about this line equals 0. They are not symmetric, and this signal the CP violations. They're CP violating because the CP even coefficient and CP odd coefficient coexist. They can interfere to affect this phi distributions. Okay, so I illustrate in more details, and that we did a Monte Carlo for this to measure this scenario S6. These are 3 input parameters that I had: 0.032, 0.1, 0.1. Now, how much event I should do in the simulation? So I just get a upper limit from this. Well, as I've said, both LHC experiments have been trying to look for CC and the 4 charge lepton. There's some upper limit for this market range for about 260. They're roughly less than about 0.1 picobar. So based on 0.1 picobar, I multiply by branching ratios and so on, luminosity, about 1,000. So in the following, I use 1,000 events in our simulations. Okay? And assume the resolution is about 0.1 for cosine theta and 0.1 pi for phi. Okay. Okay, so these are the cosine theta distribution I got out from the Monte Carlo. These are the best fit. Okay. And this is phi distributions. You can see, again, this is not symmetric, about 0. This is some kind of CP violation. And these R1, R3, the first row, are the input to this Monte Carlo. And output value, well, this just happen to be the same, but these are different. The output value from the fitting actually is not the same as the input value. But basically, they are mostly within about one second. All right. Same. This one, well, plus and minus, but the error are large. This is about 2 seconds. So. And these R1, R3 actually are correlating. Now, how about the actual input parameter? Originally, we have these 3 input parameters. Sorry, these 3 input parameters: 0.03, 0.1, remember that? And what are the values that we can get out from this Monte Carlo? So 0.032. Now for the best fit, I get 0.03, and the error is about 10%, or slightly more than 10% or 12%. And for this one, the input value is 0.1, so I got 0.078 plus or minus 0.17 is a 1, about slightly more than 1 sigma. And this one is also within 1 sigma. This 0.1 now become 0.11. So the uncertainty I can get out from 1,000 events at 12 to 20% from this Monte Carlo. Of course, in this diagram you can see 68%, 95%, 99% confidence level for this parameter in this like P and G plane and S and H plane. And this one-dimensional chi-square distributions. Again, we can read off the 1 sigma, 2 sigma, 3 sigma. Now, actually, we can do slightly more events. For example, I take out this graph from Atlas. This is a conference note. Like, so the upper limit around this region, I can say is a 0.2 to 0.4. That corresponds to about 3,000 events in high velocity of LHC. Okay. Now, if I increase to 3,000 events, okay, the uncertainty certainly, here using 1,000, 3,000, we have less uncertainty, smaller uncertainty, and the uncertainty is around 10%. Okay. So I'm going to summarize what I said here. So the angular distribution of theta 1, phi, that are defined in the rest frame of the Higgs go to 2 C bosons, and each C boson decay into 2 charged electrons. We can, based on these angles, we can fit to the observable Ri, and then the fit to the original Higgs couplings. Okay, the G, C, and S and P. All right. Now with the 1,000 Higgs events, one can then determine this to about 12 to about 20% uncertainty. Okay. Now with 3,000, it can go down to 10, about 10% uncertainty. In the fit, there are some like R2, C2 does not appear. If there's a pair of C2, which means that there are some new particles with mass less than m Higgs go to 2 running the loop, which means that there's some develop some absorptive part. Okay. Now, in order to see some other observable like R6 and 7 that I did not show here, we need to go beyond one-dimensional distribution. We need to like 2-dimensional distribution in order to see the observables. Okay, that's all I'm prepared here. Thank you.
Thanks, Kingman. It's time to.
So this projection about 1,000 Higgs and this is for 260 GeV Higgs
Yes.
specifically.
Yeah, 260 basically.
So, but this does depend on the Higgs mass, right?
Yes. For example, this is the upper limit from this conference note of early this year. For what this is 300, 250. So around here, at most you can stretch it to about 0.7. So I just take basically 0.2.
Yeah, but I'm just saying that in general, for heavier Higgs, you mean this projection will change for heavier Higgs.
Yeah, sure. Well, maybe in 2 years, 2 years time, the limit getting lower, you expect less than 1,000. Now, but you can still do some, for example, 500. You can still do not too bad, I guess, 20 to 30% uncertainty.
So for 260 to have a 3,000 or 1,000 event, what kind of so this also goes through top loop, right? This is the production is also goes through top loop.
Oh yes. Well, we do not assume anything here. Just assume we have 1,000 events. Yeah.
Well, it has to be produced
Basically,
at some point, right?
This Higgs is just produced by Coulomb field fusion. That's what we assume.
And this couples to top because it mixed with the Higgs.
Well, you can say that, yes.
Okay.
Yeah.
Yeah, because it has to mix with Higgs. Otherwise,
Yeah,
otherwise it don't
cannot
decay
control.
back down to ZZ anymore.
Yeah, otherwise you cannot
Yeah.
produce it. Yes. Yeah.
Okay. All right.
Thank you.
Any other question? If not,